Hello and welcome. This is Dr. Himayatullah Khan, and today I welcome you to my video on Johansson co-integration test and vector autoregression model. Uh, Now, in my previous video, you might have watched that if there is a long run relationship among the time series variables, then I will estimate vector error correction model. But if there is if there is no Johansson co-integration among the four time series variables, then in that case I will estimate VAR rather than VECM. So let me first open my data file, that is the same file, and it has a number of variables, that is consumer price index, IP is industrial production, M1 money supply, and T bill is a treasury bill. Now, first of all, I would like to open this as a system, as a group, and here are four of my variables. Uh, in my previous video, you saw that there was a co-integration among my four variables, and then I did vector error correction mechanism. But let us assume that there is no co-integration, there is no Johansson co-integration among these four variables. Then in that case, I will not estimate VECM, but rather I will estimate VAR, that is vector autoregressive regression equation. So let us suppose that there is no co-integration among these four variables. So I would like to estimate the VAR system. So how can I do that? Let me go to Quick, and under Quick I will go to estimate VAR, and this time I will check unrestricted VAR, and here I will give list of my variables. So my one variable is CPI, another one is IP, another one is M1, and my last variable is T bill, that is treasury bill. Now I will press OK, and when I press OK, I get this vector autoregression estimates. Now you see that here my this is autoregression vector autoregression estimates, and there are four equations. That is CPI, and CPI is regressed on CPI in its first leg, CPI in its two leg, and then industrial production first leg, second leg, money supply first leg, second leg, and treasury bill first leg and second leg, and this is the intercept or constant terms. And also the other variables have also the same explanative variables in their own constant terms. These coefficients have standard errors as well as their t statistics, but they don't have p values. So how can we do that? How can we have p values for these um, models? So let me go to Quick, and okay, let me be on the equation page, and click on proc and make system, and system order by variables, and let me click this one, copy from here, and I will paste it in Quick estimate equation, and paste here. After pasting this, I will press OK, and when I press OK, I get my vector autoregression estimates for the first equation, that is CPI. So here my dependent variable is CPI, and the method that I use is least square, and the total number of observations after adjustments are 622. CPI is regressed on the coefficient, and CPI in its first leg, CPI in its second leg, industrial production in first leg and second leg. Then I have money supply in its first leg and money supply in its second leg. Similarly, treasury bill first leg and second leg, and the last one is my constant term. So I have, these are the coefficients and their numerical estimates, these are their standard errors, these are the t statistics, and now you also have p values for these coefficients. So C1 is significant, C2 is significant, C7 is significant, and C9 is significant. Rest of the coefficients are not significant. You see one difference between this estimated equation and the one that we did in the previous video. This doesn't have vector. This equation, this estimated equation, doesn't include error correction mechanism or error correction coefficient, because there is no cointegration, and there is no short run adjustment to the long run equilibrium. But in this video, we assume that there is no cointegration. So VAR basically shows long run relationship among these variables. So this is how we check, how we estimate VAR model when there is no co-integration among the time series variable. Now we can also check our coefficient diagnostics here. If you like, you can do that by VAR test, and you can also check omitted variable test. You can also check for redundant variable test and others. But the most important one is that of residual diagnostics, and here we can check normality and histogram of the error term, and we can also check serial correlation of the error term and heteroscedasticity test. So let me first do this, and this is the Jarka-Bera test, and it shows that this the error terms are not normally distributed, because we can easily reject the null hypothesis on the basis of the Jarka-Bera p-value. Okay, so after doing this, let me check. Let me check for serial correlation. So again, go to serial LM test and leg 2, and this basically gives me F statistics and observed R squared, and this is the Bruch-Godfrey serial correlation Lagrangian multiplier test. And the null hypothesis is that there is no serial correlation among the various values of the error term, and the null hypothesis is rejected on the basis of the chi-square p-value. So I mean, this model suffers from serial correlation. We can also look at the heteroscedasticity of the error term, and for that I would like to use White test. And if I do that, let me press OK, and again there is F statistics, the observed R square statistics, and scared explains SS, and the probability of chi-square basically reject our null hypothesis of no heteroscedasticity. Now, although we estimated VAR model for CPI, but this is not a very good model, because it didn't pass the test of normality of the error, it didn't pass the test of serial correlation, no serial correlation, and heteroscedasticity test. But this is how we can estimate VAR, that is vector autoregressive function or equation, when there is no co-integration among the time series variables yeah. So I hope you could have got some idea of how can we estimate vector autoregressive estimates, and how can we check the residual statistics diagnostics, and we can also check stability diagnostics of the system too. But I hope this is okay. Thank you.